So thanks for introducing me and thanks for the invitation to speak. So today I'm going to talk about possible sizes of sumsets. So for a outline of my talk, I'm going to start by talking about missing sumset sizes, so things which can't be achieved as h-fold sumset of k integers. Then I will specialize to threefold sumset sizes. Um, The case of twofold sumset sizes is due to Erdos and Semiretti, but I'll describe a complete result on threefold sumset sizes. Then I will go to h-fold sumset sizes for bigger h and talk about how it works there. Um, then I'll briefly mention a story involving ChatGPT and Tim Gowers. I guess AI has been mentioned in many of these talks, but I will, yeah, give a couple remarks about that, and then I will talk about future directions. So to get started, let's define h-fold sumset. So if A is a set of integers, the h-fold sumset of A is all of the things you can make by adding up h different elements from the set A. I imagine this set has appeared in many other people's talks, but let's look at a couple examples. So if A is the set of five integers 0 through 4, then 3A is going to be the whole interval from 0 to 12. And so the size of the set 3A will be 13. But the size of the set 3A is going to vary if we change what A is. So if we let A be, for example, 0, 2, 3, 4, 5, then if you add up three of these, you can get 0 as 0 plus 0 plus 0, 2 as 0 plus 0 plus 2, etc. And you get everything from 0 to 15 except 2, and sorry, except 1. And it's clear that you can't get 1 because A is positive integers plus 0, but there's no 1 in it. And so here the size of the set 3A is 15. So we notice that changing the set A, even if it has size 5, can change the size of 3A. So these are examples of sets with small sumsets. And if we look at a set with a bigger sumset, for example, powers of 4, then 3A is going to be much larger. And the reason is that we have less overlaps. So for example, in the second example, 4 plus 4 is equal to 5 plus 3, but we don't have things like that occurring with powers of 4. And so what happens is the number of threefold sumsets is the number of ways to choose three elements of A with repetition allowed. And this is described by stars and bars to be 5, which is the size of A, plus 3 minus 1, choose 3. And so it's 35. And so seeing the way that the size of 3A varies motivates the following definition due to Nathanson, which is R of HK is if we look at all sets A of K integers, what are the possible sizes of the sumset HA? And so from the last slide, we saw that 13, 15, and 35 are all examples of elements of R of 3, 5. And it turns out that R of 3, 5 is going to be the whole interval from 13 to 35 minus the point 14. So it turns out we can get everything between 15 and 35. We can't get bigger than 35. We can't get less than 13. And interestingly, we can't get 14. So I guess the work in this talk is going to be studying R of HK. So first thing we can observe is that R of HK sits inside an interval from HK minus H plus 1 to H plus K minus 1, choose H. And the endpoints of this interval are both achieved. The lower endpoint comes from an example like on the previous slide where A is a arithmetic progression with K terms, or for example, 0 through K minus 1. And as we saw in the previous slide, H times this set will have size given by HK minus H plus 1. And the maximum size of these sumsets will be achieved when there's no additive relations of size h between the elements of A. So for example, if A is powers of h plus 1, then we'll get this maximum size, h plus k minus 1, choose h. And it's sort of a stars and bars argument to show that you can't get more than this. Okay, so we know an interval that R of HK sits in. So what can we say about sort of missing sizes, things which are missing from this interval? So we can look at an example. R of 6, 7 is bounded between 37 and 924. And the first work related to R of HK was by Nathanson, who showed that if we let M be the smallest element of R of HK, then M plus 1 is sort of like a missing size. It's a gap in R of HK. That's like how on the last slide, 14 was missing from R of 3, 5. And this result was extended due to Skinina in sorry if I'm mispronouncing that, last year. And he extends this missing value to a missing interval. So here we have a interval of h minus 2 elements, and none of them can be possible sumset sizes of a six-fold sum of 7 integers. Yeah, so this shows that there's some complexity going on here. And in my work, I was able to extend this missing interval to a missing triangle. So you can ignore the definition in red. It's kind of a annoying computational formula for this triangle. But the way you should visualize this is we have rows of size 6, rows of length h, and we put M in the top right corner. And then we sort of draw this triangle in the second row, ignoring the like rightmost two columns. Then we draw this triangle, and none of these elements can be in R of HK. So I guess in this case, it extends Skinina's four missing sizes of sumsets to 10. The way I prove this is using the diameter of the sets. So the diameter of a set is basically like the smallest arithmetic progression which contains a set. So sort of like how much space on the real or on the number line this set will take up if you write it down like starting at 0. And there's results due to Lev from the 1990s which say how the diameter of a set controls the size of its h-fold sumset. And so using this result allows one to rule out this triangle of points. Yeah, so I guess you might be thinking like, it's nice to rule out these points, but who cares? We had 4 missing points before. Now we have 10 missing points, but there's still 900 possible sizes. But yeah, and sorry, I call this triangle delta HK because it forms a triangle. But when I looked at numerical data, it seems like actually every other size in the interval is achievable. So I made a conjecture that R of HK is actually the whole interval minus this missing triangle. So this interval has on the order of like k to the h elements, and the triangle has h minus 1 choose 2 elements. And I conjecture these are the only missing ones as long as k is bigger than h. And so the remainder of the talk is going to be about sort of progress towards this conjecture. I'm able to prove it when h is 3, and I'm able to prove it when h is fixed and k is sufficiently large. And so I'm sort of going to tell the story of how these proofs came about. But yeah, before I continue, are there any questions about anything so far?
No.
Okay, let's keep going. So the first work towards this is by Erdos and Semiretti in the 80s. And they showed that R of 2k is the whole interval from 2k minus 1 to k plus 1 choose 2. So these are twofold sumsets of k integers. And actually, they didn't say this as a theorem. They stated it as a remark. We see that it is easy to see that you can achieve all of these values as twofold sumset sizes. And so I guess Mel told me that Kevin O'Brien pointed him out towards this remark, and then um, Mel wrote up a proof. It's a clean inductive argument. It's not a long proof, but this is well, it's not a triviality, let's just say. You need some inductive argument and you need some construction involving like an interval, the unit of an interval with another point outside the interval, and that's sort of like the base of the inductive construction. Um, but yeah, so this is R of 2K, and in my work, I'm able to extend this result to R of 3K. So I show that for all K, the set of threefold sumset sizes is the whole interval except for 3K minus 1. So this was like that missing 14 a couple slides ago. It was like all the way from 13 to 35, except 14 is missing. Yeah, so now I'm going to, I guess, briefly talk about the proof idea of this. So the first thing I noticed was if you want to study the size of 3A for various sets A, you also need to study the size of 2A. You can't really, and the reason for this is because 3A is A plus 2A. And so before you can understand 3A, you have to understand 2A. And so I made a bunch of plots like the one on the right, where I take all the sets of 6 integers. And on the x-axis, I plot the size of 2A. And on the y-axis, I plot the size of 3A. And you get a lot of interesting structure going on here. There's different inequalities satisfied like Planck-Ruza, but those aren't really that tight. And so, yeah, it's not clear exactly where all these dots are appearing. But the thing we want to prove is that sort of all of the y values from 18 up to 56 are going to be achieved. We want to prove that R of 3, 6 is everything from 16 to 56 except for 17. And so to prove that all of these y values are achieved, well, like in the h equals 2 case, we want to induct on K. But what's the right inductive hypothesis? It took a bit to come up with it because it's not, you can't, I don't think it's possible to do this using the sort of simplest possible inductive hypothesis, like, oh, this theorem is true for K minus 1. Turns out the inductive hypothesis I was able to make work is something about there existing a path going from the bottom to the top. So what do I mean by a path? I mean that from each vertex to the next, I either go up by 1 or up by 1 and to the right by 1. And so somehow, even though we're only interested in studying 3A, our inductive hypothesis also has to include the data of 2A. And yeah, so I think it's quite a subtle inductive hypothesis. But once I have this inductive hypothesis idea, then it's not that hard to carry out the induction. So the way to do it is start with all of the sets of K minus 1 elements. Let's call one of them A. And for each set of K minus 1 elements A, let's say it's between 0 and D, with D being an element of A. So that's just by translating it to be positive and contain 0, or sorry, non-negative and contain 0. Then we construct 2 more sets by combining A with the point 3D and A with the point 3D plus 1. And if we take all the sets A of K minus 1 elements and we construct A prime and A hat, which are going to be sets of K elements, it turns out that if the sets like of size 6 contain this red path going from the bottom to the top, then we make the sets of size 7 using these constructions, and we again get a red path going from the bottom to the top. And so we're golden because we've already ruled out like 3K minus 1 using stuff from the previous couple slides. And so this gives a complete result on what are all the sizes of threefold sumsets of K integers. Okay, so what's next? The obvious thing to do is to try to extend this to h equals 4. So with h equals 4, the plot becomes more complicated. You should think of this as like a 3-dimensional plot. So the y-axis is the size of 4a, the x-axis is the size of 3a, and the color is the size of 2a, where here we look at all the sets of six integers. So, as we saw in the previous slide, the uh, x-axis variables vary from 16 to 56, with 17 missing. And yeah, so there's sort of a lot going on in this plot. We really hope to be able to do some similar construction with a path going from the bottom up to the top, because this plot does look quite connected. But unfortunately, I wasn't able to carry out an inductive strategy on this. Somehow with h equals 3, we were only controlling 3a and 2a, and that was doable. But to control 4a, 3a, and 2a all separately, yeah, I couldn't find a way to do it. And so I was quite stuck on this for a while, on how to extend this work to general h equals 4, h equals 5, etc. Again, we have this conjecture that as long as k is bigger than h, R of hk is the whole interval minus that missing triangle. But after a lot of work, I was able to prove this conjecture for k sufficiently large. So fix any natural number h equals 4, 5, 6, etc. And for k sufficiently large, R of hk turns out to be the whole interval minus these missing points. Yeah, so this is, yeah, so how on earth would we go about proving this? Yeah, so the first thing is that these missing points, there's only h minus 1 choose 2 of them. And so k is going to be much larger than h. So almost the whole interval is going to be achieved. Sort of the challenge is not ruling out these points or what goes on around them. It's sort of like achieving the whole interval in the middle. So how do we do this? The main lemma, which is, I guess, the main technical lemma, is that for any epsilon bigger than 0 and k sufficiently large, you can get everything above epsilon k to the h achieved. And so, yeah, I'm not going to have time to, I guess, like give the whole idea of the proof, but I'm going to sketch the construction. So we want to build sets A of size k, A1, A2 up to AR, by combining smaller components. And what are these components going to look like? So basically the idea is to get things which have sort of sumset sizes in the middle, we want to combine components with small sizes of sumsets and large sizes. So the component with small sizes is an arithmetic progression plus a point. And so this is sort of going to have a very small h-fold sumset size. And then we want to combine this with something with a bigger sumset size. And so the component I looked at is a geometric series. So we consider geometric series with common ratio m. So common ratio 2, common ratio 3, common ratio 4, up to common ratio h. And sort of each of these has sort of its own characteristics of its h-fold sumset sizes. And this is almost enough, but it turns out I also needed to consider geometric series without the number 0. And these behave a little bit differently. And then the way I construct these sets A is I combine all these components and I vary all of these parameters, B, J, S2, S3 up to SH, and T2, T3 up to TH. So we vary sort of like the sizes of the geometric series and the sizes of the arithmetic progression. And yeah, so why on earth does this work? The way that I think about it is I think about it like when you're setting a clock, you first set the hours hand to like a vague precision of what time it is. And then you set the minutes hand, and that gives you like some more specific precision. And then you set the seconds hand, and this gives you, precision up to the second. And so by setting the hour hand, minute hand, and second hand, you can construct every possible time in a 12-hour scale. And so I think about this similarly. So B and J are sort of like the hours hand, like they control sort of like the big picture behavior of the sum set size. And then these guys like S2, S3, T2, T3, these are like the minute hand, like they do sort of a medium size of control. And then like SH is going to be the seconds hand. If you change SH by one, the sum set size will change by one. And so as long as you set the hours hand and then the minute hand and then the second hand, you can get every possible time. And you have a similar thing with these sum set sizes. And I also think about it in a similar way to like a intermediate value theorem. But yeah, using this sort of idea, you show that the set of all of these sum set sizes forms an interval. And then we're basically done because we show there's an element of this interval that's less than this, and an element of this interval that's more than this. And so this gives us our result. Okay, so let's continue on to a new question where we optimize the diameter of the constructions. So another parameter we can think about is what is the minimum n such that we can get all of the possible sum set sizes by only considering A as a subset of the interval from 0 to n. And so Nathanson introduced this, and sort of is a very funny story. Tim Gowers was playing around with ChatGPT, putting in various Nathanson problems. And sorry. The first thing is using general techniques. Nathanson gets a bound on this, which is exponential in k. And yeah, when playing around with, so I'm going to state theorem, which is that n of hk is polynomial in k. And there's I guess, strange authors of this theorem. It's ChatGPT, Gowers, and me. And ChatGPT is first, which is deserved because the bulk of this work came from ChatGPT. But basically, Tim Gowers was putting in problem of determining n of hk into GPT, and GPT came back with something like exponential in square root of k. And he sent this to Mel saying, GPT has done this. Then Mel sent this to me. And I thought, well, this improvement to exponential in root k is not all that impressive, but it's definitely correct. And I gave sort of a vague suggestion for how you could possibly improve this to polynomial in k. But I didn't see a path to doing this. But to my surprise, a few hours later, Tim Gowers comes back with a GPT proof that n of hk is polynomial in k. And once I saw this proof, I was sort of immediately convinced. And yeah, so Tim and I wrote a blog about this, about sort of like this specific construction, and then also like the future of AI and math, and like how AI is changing math. Yes, there's a lot of thoughts there, which I won't talk about here. But I guess the main idea of the proof is to replace these geometric series from the previous slide, which have sort of diameter exponential in L, where L can be around the size of K. Replace these by sets with similar sum set sizes formed by BH squared sets, so H squared dissociated sets. And these can have sort of polynomial diameter, and you can sort of achieve a similar construction using polynomial diameter, which was like a simple idea, but a very clever one, which ChatGPT came up with. Okay, so with my last couple minutes, I want to get into some future directions. So one thing is you can optimize KH, which is how big K has to be so that the main theorem holds. Another thing is you can study R of HK when H is bigger than K. I know that Mel has done a lot of work on this, as have O'Brien, Sanger, many other people. But it's much more complicated because R of HK doesn't look like a whole interval when H is getting large. you can, well, you can try to extend the h equals 3 method to that colorful h equals 4 plot. Um, you can work in groups with torsion. So like Z mod M to the N, then you're going to have a lot of different structure. My work should hold for any infinite torsion free abelian group, but yeah, there's a lot more structure in groups with torsion, which makes this complicated. Um, Another thing is you can work with restricted sumsets. So here we're looking at sums of H elements where we are assuming that AI is different from AJ if I is not equal to J. And another thing is to, I guess, study these plots that I showed further. And then finally, I guess I want to end with one like moonshot future direction, which is kind of seeing if there's some connection to graph theory. So on the right, I have in the limit as n gets large, the on the x-axis, the number of edges of graphs on n vertices divided by n choose 2. On the y-axis, the number of triangles on n vertices divided by n choose 3. And you get this interesting plot, which was proved by Razborov about 20 years ago. And I'd be very interested in the limit as a gets large, whether the 2a, 3a plot will approach something similar. It would be very stunning if there's a similar type of result for the sum set sizes as for the graphs, because this gives a bridge between additive combinatorics and graph theory. So I'm out of time. Thanks for listening. And I'm going to put up some acknowledgements. But yeah, thank you very much.
All right, thank you, Isaac. Any questions for our speaker? Yes.
So Isaac, I don't know, can you hear me?
Yes.
All right, this is Steve Sanger. I'm probably going to send you an email with some more concrete things to say, but first, a silly question. Have you heard of anyone considering, instead of just iterated sum sets, potentially, sums of two sets? So A and B instead of just A.
Yeah. I have not thought about this. So is there any relation in structure between A and B?
I don't know. I've seen Mel speak on this numerous times, and this is the first time I've thought about it.
Yeah, great. Yeah, so I think there's results on sort of like the smaller end of the interval. Like, so for A plus A, there's Feynman's 3K minus 3 theorem, and there's sort of an analogous version of that due to like Levin-Smilyansky with A and B. But I don't know of any results about the possible sum set sizes. That would be, I think, a very interesting question. If A is a set of K integers and L is a set, and B is a set of L integers, what are all the sizes of A plus B? It seems quite interesting. And yeah, so that's a great question.
I might email you further if I come up with anything. And second is more of a comment than a question. I think when you go to H equals, or sorry, when you go to H equals 4, you can say the plot thickens.
Oh, that's funny.
Other questions for our speaker? Yeah.
So I don't do any of this. This is, I think, a rather naive question. Does anything special happen if H is almost K? If H is K minus 1?
When H is K minus 1? Yeah. I guess so. So this triangle has sort of the number of rows is the minimum of H and K minus 2. And so when H is bigger than K, so like K is H minus 1, then this triangle will become a trapezoid, like it'll be missing the lowest vertex. And yeah, so when K is just a bit less than H, this triangle sort of looks like a trapezoid. But you can extend this triangle to like a different polygonal figure, which is, I guess, a bit hard to describe, but maybe I'll try to you have like a trapezoid, and then you have like another trapezoid on top where the diagonal has slope 1/2, and then another trapezoid below that where the diagonal has slope 1/3, etc. Um, and this comes from a result of Lev from the 90s. Yeah, actually, yeah, I guess I didn't know about this paper of Lev when I wrote the draft of this. Is currently on the archive. But there's sort of a published version of my paper which is going to appear on the archive this evening, which has sort of a discussion of this in section 5.2. But it's sort of like there's, yeah, you can generalize this triangle a bit, but it's not clear, I guess, what happens outside the generalized triangle.
Other questions for our speaker? So
I,
Isaac, are you going to be a senior next year?
I'm going to be a senior, yeah.
Right, okay. All right, let's thank our speaker again. And the next talk will be as soon as, oh, I'm sorry. Yeah, Isaac, if you can check the chat, I don't know if there's something for you.
Oh,
or-
yes. I'll respond to that in the chat. Yeah.